So I would like first to thank the organizer for inviting me. It's really exciting for me to take part in this spectroscopy meeting. I'm a string theorist, and I'm not often exposed to this region, to this domain of research. Even though in the last 2 years, what I've been working on is applying string theory exactly to this issue of hadron physics. What I'll describe today is mainly done in collaboration with my student Doreen Weissman, and I'll start with just presenting this cartoon of the different techniques and methods that were implied through the years to understand hadron physics. So we started with all the Regis theory, and then we've heard a lot about the quark model, and needless to say that QCD is the main domain to analyze hadron physics. On the other side, we have also large N of QCD, which led to the Skir model, chiral Lagrangian. Supersymmetry was suggested as a simplifying framework to understand gluon dynamics, and in 97, Maldacena came out with this idea of a gauge of gravity correspondence or holographic duality. And what I'll describe today is a simplified model, which I refer to as holography-inspired stringy hadron model, which is based on the old Regis theory and some ideas of QCD and mainly of holography. Okay, so the reason that I'm going back to, in fact, the old ideas of hadrons and strings is because I think that even until now, the way to describe meson spectroscopy is much easier when one treats them as strings than any attempt to get the spectrum from lattice QCD or from other methods. The stringy picture is essentially very simple and therefore I think very appealing, at least to me. Okay, so let me tell you briefly about this Hish model, the holography-inspired stringy hadron model. I won't be able to show you how I derived it. If I'll have time at the end of the talk, I'll briefly explain it, but I'll now state the main results of this model, and then I'll devote most of the time to applying these results, predictions to fits and of the PDG data. So a meson is simply described by an open string with massive endpoint particles. If you want a quark and anti-quark on its end, a baryon is an open string with a quark on one side and a diquark on the other side. Of course, it could have been also the Y shape of three strings, but there are good reasons from theory and more importantly from observation to believe that it is a string with a diquark and a quark. Now, glue ball is a closed string, and tetraquarks will be described as open string between a baryonic vertex with a diquark on the one side and the anti-baryonic vertex and an anti-diquark on the other side. Now, in a cartoon way, I mean, these are the holographic descriptions in terms of flavor bands, D and U flavor bands for the light case, which, as I said, maybe I'll come back to it at the end of the talk. So in the holographic picture, in the 5 or 10 dimensional, that is a string that describes a meson of charge minus, a meson, neutral mesons, and so on. And with the baryons, we will have a diquark on one side and a quark on the other side. This is in the way that the holography will describe them. And this is the picture in Hish, where we map the higher dimensional curved space-time to 4-dimensional flat space-time. So basically, this baryon will be B plus will be described by a string with a with a DD, sorry, by B minus DD diquark on one hand and a D on the other side. Okay, so now how do we get the spectra of the hadron in this stringy picture? So we have, of course, a ground state, and we have excited state both with angular momentum and with radial excitation. So the basic idea is that there is this string, and there should be some balancing between the tension and so the forces that act on the quarks will be indeed a tension, but there is also a repulsive Casimir force that balances this tension. In that way, the string does not collapse to zero size. As you know well, in open string, bosonic open string, the ground state is tachyonic, but rather here in these hadronic strings, since we have a repulsive Casimir, or in the language of this intercept, it's a negative intercept, then we have this balancing between the tension and between this repulsive Casimir force. And from that, we get simply that the tension times the length is the square root of the intercept over alpha prime. And so altogether, what we get is that the ground state mass will be simply the mass, the endpoint masses of one quark and another, plus the contribution to the mass that comes from the string, which for light quarks is the dominant one. So the strings are clearly much less important. And so it's M1 plus M2 plus the square root of the intercept over alpha prime. In a moment, I'll explain in more details what is the intercept. Now, for excited states with angular momentum, we can first do the classical relativistic picture of a rotating string, and that's the energy that we will get in terms of the masses of the endpoint particles, the length of the segments of the arms, the velocities of the endpoint particles, and the tension, of course, and similarly, we have this expression for the angular momentum. When we go quantum mechanically, then this classical expression is simply replaced by adding the intercept, which in our model will be a complicated function of the mass. But I mean, if people remember, in the ordinary structure, A is just one. Okay. Now this is a parametric description of the relation between the angular momentum and the mass. If we take the small mass limit when beta I, the velocity of the particles and the endpoints goes to 1, then we get a simple modification of the Regge result. So the Regge result, well known, is that J is alpha prime E squared or M squared, and now it will be multiplied by this correction, where the corrections are proportional to the ratio between the mass of the endpoints and the mass of the hadron. Now, in the other limit where the mass of the endpoints is large, so the major contribution to the mass of the hadron comes from the mass of the quarks is large, the endpoints, then we'll get this expression. This is the approximation of the previous expression for the case of like when we have C or B quarks. Okay, so now the intercept is a signature of the quantization of the system. So we started with a classical rotating or non-rotating system, and we add the quantum fluctuation, we quantize them, and we get that there is a Casimir energy, which is just a sum over the Eigen Frequencies, which takes the form of A times pi over L. L is the size of the string. For the case, the ordinary case, this Casimir is just the ordinary sum over n, so that's the famous zeta function regularization, and we get -1/12, and so that's the expression for ordinary strings. But now for the strings with massive endpoints, the Eigen Frequencies are determined by this transcendental equation, where the solution looks like that. So this is expressed in terms of 1/q. Q is m over TL. So we start, for instance, for n equal to 4 omega, and for very heavy very heavy quark mass, and we go to 3, and then from 3 to 2, and so on. So this is what one has to solve these eigen frequencies, and that's a modification which enters in the spectrum, of course, and also in the expression for the intercept. Now, we have also radially, or we have excitations which are not related to the angular momentum. And then in the ordinary string, it was that n, the excitation number is alpha prime m squared. This is the dimensional quantity plus the intercept. And now with massive endpoints, this is replaced by omega and eigen frequencies equal to that. And we calculated the intercept as a function of the endpoint masses, but I won't go into all these details. Now, another aspect of this model, which is not related to the spectrum, to the spectra, is the decay width, the strong decay width. And one has to do for that string calculation. In fact, using the optical theorem, it's a string one loop calculation. I won't describe the details, but the final result is in fact very simple, and it tells us that the total decay width of the hadron should be linearly proportional to the length of the string, and the length, as I showed you before, is simply related to the mass. So there is a simple relation between the total decay width of the string, which is supposed to describe the hadron, and the total mass of it. Now we have to supplement this by a phase factor, but this is basically the total width of a decay of a hadron. Now, if you want to instead of the total width consider the branching ratio, then if we break the string as was demonstrated here, we start with a string, it breaks into 2 strings, and in these endpoints we generate a quark-anti-quark pair, and so in that case, the probability for such a transition is proportional to the exponent of e to the minus m squared over t. M are the masses of these endpoint particles, and t is the tension. So we have some very simple results for the spectrum and for the decay width. So this is a way, by the way, a way to determine this ratio, which is sometimes referred to the Schwinger mechanism of creating a quark-anti-quark pair in a flux tube. This was done by my colleagues, the late Aaron Kasher and Shmuel Nusinov and Herbert Neuberger, many years ago in the context of QCD. So we have an expression for the branching ratio, we have an expression for the total width, and we have these formulas for the spectra. And now we want to go ahead and describe it in terms of and fit it. So I'll now jump over all this derivation, which, as I said, I'll come back to if I have time at the end. And I want to go to the second part, which is the fit of the Hish model to experimental data and certain predictions. So we'll do this fit to mesons, baryons, gluons. This is, I think, very important topic, and also tetraquarks and other exotic hadrons. So let's start with the fit to mesonic spectrum. So we took this long list of mesons which follow the trajectory of phi b, OA, eta h, omega f, and so on, and also including heavy quarks. And we started to see how well the trajectory of this modified Hish model, we call it a holographic modified radio trajectory, how it fits the data. So the blue dots are experimental values, and the line is the model, and the red points are just the values of the model at a particular angular momentum. So we start with the isospin singlet omega and eta, and then for the isospin vector for the rho and pi, we have this trajectory, so that will be for the rho, and this is for the pi. This is a very important point that the pi itself does not fit well the trajectory of the pi meson. It's much below the trajectory. Well, that's probably related to the fact that it's a Goldstone boson, but the rest of the pion states are fit very well. So far, it seems that all these trajectories are very linear. When we go to heavier quark masses, like for K and K star, you see that we start to get bending. Here there are some discrepancies in the K between the line and the experimental data. We have for the phi, and then that is more interesting because that shows explicitly the deviation from linearity. So that's not anymore radial trajectories, but they fit quite nicely the D and the S and the D star and D star S. And also when we go to Charmonia and B and BS, and it's all, the plots are all m squared as a function of the angular momentum. And one can also similarly do plots of m squared as a function of the radial excitation number n, but I won't display them now. But anyhow, you see that we get trajectories which are not linear, but they fit quite nicely the PDG data. And so altogether, when we summarize this, all the trajectories, we extracted the parameters of the best fit parameters, and we get the masses of these endpoint particles, which come out from the fit to be 60 MeV for the light quarks, roughly 200 for the strange, and 1500 for the char. And you see that these results are neither the constituent quark masses nor the QCD ones. This is what the fit to these string endpoint masses give us. And it's important that it's a new concept of a mass of the particle, which I refer as a string endpoint mass. Okay. Now we also extract alpha prime, which is 0.9, and a bunch of intercepts which relate to each of the trajectories. So the number of fitted parameters is, of course, much smaller than the total number of points that we can fit. Now, one thing which is interesting is that we look on the best fit as a function of M1 and M2, we get this red line, which obeys this M1 to the third 3/2 and M2 to the 3/2, and that is, if you remember, this was exactly what we predicted as the first correction for the. Sorry, just a second. So here you see we get that the corrections are the quark masses, endpoint masses as a 3/2, and indeed the fit to the data confirms this this value. Okay, so let me make some comments about the spectra. First, about the spectra of light. Hadrons made of light quarks, and then for heavy light and so on. So the trajectory with the light are very nearly linear. For when once you introduce the strange, there are deviations from linearity. And there are some cases, K3 and K4 in the trajectory, as I showed you, do not sit nicely on the trajectory, and we don't have an explanation for that. K star fit much better. Okay, now for the light heavy, we have the deviation from linearity that I showed you, and we can use these trajectories to predict several of the quantum numbers of resonances that were discovered, and the quantum numbers of them were not determined. For instance, this resonance we claim should be 2 minus. And well, about the spectrum of Browconia, we get that it's still with the same tension or alpha prime as for the light one, which is well, not so obvious, because when we have this heavy quarks, the picture in holography changes quite dramatically. But still, for the J m squared, it's still 0.9. But when we go to the m squared n, it's one has to use a very different alpha prime. The reason for that is that this omega n is not anymore n. Okay, and we have also interpolation that we've done. Well, we can look for the states which are built of B quark and C quark, and they will have a slope which interpolates between the slopes of the bottomonium. This is, I think, an important point in my talk, that I can now take these trajectories and present predictions. So if we take the pi b trajectory, we predict that there should be a 5 plus minus with this mass and with this width. Similarly for the eta rho, and you see a long list. So at any trajectory, we can go one or more. Typically, they become wide, you see, but we can go and predict the masses and the width of higher excited states. And so we do it for both the angular momentum. So here we go to, for instance, J equal to 6. And also we can do it for a given J, we go to higher excited state. So this is the 6th excited state, the 4th, the 5th, and so on, which are above and which describe states that were not discovered yet. Well, it would be very interesting to see whether one can find them, or maybe not. Maybe because of this wide nature of them, it's difficult to detect them. Now let me proceed and go to fits of the baryon. Baryon, as I told you, I describe as a string with a diquark quark. And the main reason for that is that if you look on the for instance, nucleon or delta, then they will have the slope which is up to 5% the same slope as meson. Now, had it been this Y-shape, for instance, it should have been 2/3 of the slope of the meson. And so this is clearly excluded, and at least for excited states, I think that this trajectory will show us that the structure of baryons are a structure of diquark and a quark. Now, for the baryon, unlike the mesons, we have a phenomenon that is not fully understood, and that is that we get a different intercept for the even and odd angular momenta. Okay, but you see again, we have fits for lambda, sigma, cascade, and then lambda c and lambda b, and you see there is a very nice agreement between the fit and the results whenever there are results. And similar to the mesons, we have made predictions of the higher excited state. So, for instance, for the nucleon, we have up to 13 halves, and here is the 15 halves, 17 halves, and so on. And this is for a very long list of baryons, including those that that include bottom quarks. And again, I think that it will be very interesting to see if these predictions can be falsified or verified. And this is the same type of predictions, but now not for a higher J, but rather higher N. Okay, so let me make some comments about this spectrum of baryons. So, for instance, our model predicts the first orbitally excited state of omega will be 2050, but there is no confirmed state there. Now, maybe there is one, or the other option is that also the omega, similar to delta and n, admits this behavior of splitting of the intercept of even and odd angular momenta. Now we have the charmed baryons of lambda C and cascade C, and there is one state of sigma C with half plus and 3 halves, which are confirmed, and there is a state that was found, which is sigma C 2800, and this fits nicely to be half plus, but radially excited. There are recently, well, not so recently anymore, 5 narrow resonances of omega C were discovered, and we can also fit our trajectories. Now, there are some statements, I won't go over all of them, about this doubly charmed cascade CC. And so there is these are very simple expressions that we have for the spectrum that can be applied to many cases, and in particular to the more interesting ones with heavy quark flavor. And so let me skip all that. It is in this transparencies. You can read it afterwards. Now, I want to go now to a topic which is, I think, completely neglected and abandoned, and that is how to determine, how to identify global states. So global states in this holography and HISH are closed strings, and they are, because of that, they are different from mesons, from open strings. So in spite of the fact that they may have the same quantum numbers, they have a very different nature. And therefore, I claim that one should be able to identify blue balls, not by identifying a particle, a resonance separated by itself, but by identifying a trajectory of resonances. Okay, so this is okay. Sorry, I did. Okay, so what is the difference between the closed and open string? There are two very different and simple differences. The first is that alpha prime of a glue ball is half the one of a meson. This is very simple because a closed string is a folded string. It's like having two strings, and therefore the tension is twice, and alpha prime is half. So this is one characteristic, and the second one is that the intercept of a closed string is twice the one of an open string. So with these two differences, we claim that one can identify trajectories which won't fit mesons, but rather glue balls. Now we took the set of all flavorless hadrons. Well, some of them are confirmed, some are not, and we try to put them to fit them in meson trajectories. And one thing that we can state is that there is no way to put all of them in meson trajectories. We can suggest several splittings. Some of them are in meson and one in a global trajectory. The point is that not too many resonances on this trajectory, and that is mainly because in the region between 2.4 GeV and the CC bar threshold, there are not so many resonances identified, and we would encourage very much to look in this region, because then we will be able to check whether this hypothesis of having hypothesis of having a different trajectory, as you can see here, if we take the ground state glue ball is 1380, then it will have a trajectory, this green one, which is with a slope which is half its reverse here. Then for mesons, and once one identify here another state, then we can say that these three states are indeed glue balls. That is a very simple way to identify and disentangle glue balls from flavorless mesons. Okay, so I want to mention also that with glue balls in this stringy picture, yeah.
Can you hear me? Could you please go to the conclusion, because you already took half an hour.
Okay, so yeah, let me just briefly mention the issue of, I'm coming to the, well, I'll skip the conclusion, but I want to show you the issue of the tetra quark. So a tetra quark will be, so if this is a meson in the charmed hadron picture, and this is a baryon, then a tetra quark will be a string connecting a diquark and an anti-diquark, and that, and as we heard from Steve earlier, a main, so that there are two smoking guns of that. One is that there should be a trajectory, so we should see the whole excitation sequence, and the other one is that it should break into a baryon anti-baryon predominantly, if of course the mass is above the threshold. So let me show you this very briefly. So if we start with this tetra quark, there are two options of decaying. One is the annihilation of this BV, anti-BV, if it is below the threshold of baryon anti-baryon, but if it is above, and there is at least two examples where this is being obeyed, then the string will simply break, and we will get a baryon and anti-baryon. Okay, so I want to mention also that this predictions that we had about the decay width, the strongly decay width, that there are not too many ways in other models to compute the total decay width. It works quite nicely, and this is an indication for that we get that all these excited mesonic resonances obey this linearity. So this is the coefficient of this T times L, and you see that I don't know, up to 15% or so. So this is this coefficient, and it comes out to be very close to 0.1 for a wide range of decays, and also this explicit formula, this CNN formula or the Schwinger model formula. There are not too many cases where a strange quark anti-quark pair is being created, but in the cases that there are, then they obey this result. Okay, so let me. This is the list of people that have been collaborating in recent years about this topic, and if you have any question about Spectra, ask Hish. So I'll stop here, and I'll be happy to answer questions.
Thank you for your talk. We are a bit out of time, so I will ask if there is a very quick question, then maybe we can move more questions to the afternoon session for discussion. So is there any question or comment on this talk? Apparently not. I'm sure there are many questions, just it was really a lot of information. I can comment that I'm not so much familiar with this formalism for doing prediction, and it's quite interesting because you showed, especially for high mass, you have a very good agreement in between your prediction and the states which were found by the experiment, while for instance for lower masses, so there is a little bit of discrepancy. I'm wondering, for instance, for the DS excited mesons, DS 2317, 2460 or the others, if you evaluate the Reggie trajectories and if your prediction match the observation.
So the DS, you were asking about the DS?
Yes, DS excited states.
Yes, I believe that I can then privately discuss with you. I think that in the DS we get a nice agreement with the data, and we have a bunch of predictions about higher excited state. Yes.
Okay, no, I'm asking because these two guys, I mean, the DS2317 and 246, they're a bit out of any model. So I'm wondering if with this model, one can do the real prediction for the mass. Anyway, I'm sure there will be many more questions during the discussion in the afternoon, but now we thank you for the nice talk and we give the word to Stanley.